we are now recording. So let me, before we begin with the actual math, just talk about, oh, here they are. Somebody, name please. I'm sorry, dispatcher, John, right? Is that right? Okay. People must have been looking at these because they've been moved around some. All right. 2 weeks from yesterday, college transfer day, Birmingham West Campus, the academic building, B Hall. It's a long hallway. I think they have tables set up all up and down that hallway, and the various schools and universities will be there. That's 9:30 to 11:30. Then 2 weeks from today, if Kwame shows up, we'll have it on this campus. All right. And that will be 9:30 to 11, Thursday the 13th. And it will be on this campus, in this building. Now they say in the campus cafeteria. That's going to be awfully crowded with breakfast ending and lunch beginning and having all those tables in there. I kind of doubt it. I think they mean the faculty staff dining room, which is just next to the campus cafeteria. And in that, there's a lot more room, tables, and things like this. So that's where I'm guessing it's going to be. They may not have room for all these tables there, so they may spill out into the cafeteria or possibly the hall on the other side. But anyway, bunches of schools will be here or have been invited to be here. So try to come, and even if you're not that close to graduation, get the experience. Talk with them, find out the types of things they're looking for. They ask things that you can work on. And then if any of you are especially thinking of going into engineering, specifically mechanical, electrical, or material engineering, this is a great program, okay? It's a 10-week summer research experience. They pay you to go there. They provide free housing that I think includes free food, and they fly you there and back at least one time, okay? And then the learning experience is priceless. I mean, it's just amazing. And now, here's something that I noted later. It sort of bugged me that the application deadline was February 15th, which is a Saturday. It seemed a bit strange. And then when I opened the brochure, I opened it before but I hadn't really paid attention. They say in the brochure it's February 17th, which will be the following Monday. I think that's probably more correct. Go on and get going on it now. Get your application in as soon as possible so you can be in the running. And name, please. Marina. Trinity, right?
Yes.
All right. Anyone else come in and say a call roll? Not everybody? Okay. Now, any questions on anything we've done so far? All right. Where we left off last time was in Chapter 1, Functions of the Graphs, 1.5, Analyzing the Graphs of Functions. Here's the next thing we're going to do. Now, these, when you're looking at them, they should be pretty easy to distinguish. That when you're not looking at them and just looking at the analytical, it can be a little more complicated. What we're going to look at is when functions are increasing, when they're decreasing. Now, there's one other option, and that's when they're constant, and we'll mention that as well. This is entitled Increasing and Decreasing. Get your name, please. Huh? Okay, got it. Okay. There you go. And? Right. Great, right? All right, anyone else come in since I called roll and you didn't hear me acknowledge your name? All right, good deal. All right, so we're talking about increasing and decreasing functions. The more you know about the graph of a function, the more you know about the function itself. So here's a graph shown here. Rather a bizarre kind of function, obviously what they call a piecewise defined function. This piece is defined one way. They don't even tell us what it is, but I can make a few guesses, but don't know if I'd be right. Then this piece is defined, know what that one is, and then this piece is defined yet another way. So that's a function. It's a continuous function because there's no gaps, okay? And not only that, there are other characteristics. So what you do when you're looking at the graph of a function, always your x's are moving from lower to higher, left to right, okay? As you go left to right on x, what is the y doing? Decreasing from where? And you always refer to the x, from -2 to 0, okay? Now, if you were giving that interval, okay, and that's all you were giving, you normally would put a bracket here and a bracket here because you include the inputs. But when you're talking about these, you can do brackets, nothing wrong with that, especially if those are closed dots, but they're really interested in what's going on in between. So most of the time we only use parentheses. So this would be decreasing from -2 to 0. So assuming that's your independent variable, your x variable that you're talking about. You're not talking about y, you're talking about what the y's are doing. The y's are decreasing here from when x, your independent variable, is going from -2 to 0. Okay? Now, how would you describe this one? Constant between 0 and 2. And again, we usually just use parentheses. It's not wrong to use brackets, but they usually will express them in parentheses. And that will be constant from 0 to 2. And then what's happening? Increasing from 2 to 4. Excellent. Okay? So there you know some more things about that function. Okay? Now they say falls and constant and rises. You can use several words, but typically they use increasing and decreasing. Okay? Now, maybe it's because I'm left-handed, but sometimes I look at this and say, well, it's decreasing from 4 to 2. Well, it is, but we always go from left to right. So don't say that. Go left to right. Decreasing here, constant here, increasing there. Okay. I know you wanted to see the verbiage of this. It's so much easier looking at a graph, but here's what it means in math speak when you're writing the words for it. A function f is increasing on an interval when, for any x1 and x2 that are in that interval, okay, you got some interval here, x1 and x2 are in the interval, and always here we're assuming x1 is less than x2. x1 here, x2 here, in that interval, okay? If that's true, and this is increasing, that means f of x1 is also less than f of x2, because when x1 is less than x2, and it's an increasing function, f of x1 will also be less than f of x2. Okay, that's when it's increasing. If it's decreasing on that interval, same deal, some interval, x1, x2 are in the interval, x1 less than x2, but that implies that f of x1 is greater than f of x2 because it's a decreasing function. Okay? But a function f is constant on an interval when for any x1 and x2 that are in that interval, any x1 and x2, whichever is less than or greater than, the f1 is equal to f of x2. Okay? They're always equal. No matter which one's less or greater, they're always equal if it's constant on an interval. Make sense? A lot easier to look at the graph. Okay? So here's example 4. You tell me what's going on here. Here's f of x, x cubed. Notice there's no dots at the ends here. So what would you say? Say again. F of x What is the y doing as you go left to right on x? Increasing everywhere. If you have to give an interval, and they don't say this, but you probably do, from negative infinity to positive infinity, because these indicate they just keep on trucking. Okay? Increasing everywhere. Now, some of you may have said, no, I can't quite tell. Is that constant in here? Well, if you plug in a few numbers close to 0, like negative 0.1, cube that, you get negative 0.001, okay, which is awfully close to 0, but it's still slightly negative. Of course, 0 would be 0, and then if you plug in something else just on the other side of 0, like 0.1, cube that, 0.001. That's why it's so close, but yeah, it is still positive and increasing very, very slowly, but still increasing. So yeah, that's increasing everywhere. How about this alphabet? If using the same letter, x cubed minus 3x. Tell me what you would write. Increasing, then decreasing, then increasing. Give me the intervals. Okay? Maybe you can give me Tucker. Okay. All right. Anyone else come in and sit called up? Okay. So let's express this. Let me get my pen set up. Example 4 on page 52, section 1.5. Okay? Well, I tried to set my pen up, but it didn't go. Here we go. So this is increasing. I'm just going to abbreviate on, now, always with infinities, put parentheses. But anytime you talk about intervals of increasing, decreasing, parentheses are fine. Negative infinity to positive infinity. All right. You tell me what to write here. Going to have 3 different entries here. What was that first one? You said increasing. Where the first increase? Negative infinity up to negative 1. Okay? Then it's decreasing from negative 1 to 1. Perfect. And then finally, I don't know if I can write it, I'll try it. Increasing again. Where? 1 comma, infinity. At the bottom of the page, it doesn't write too well. That's what it appears to be doing. That is describing the behavior of that function. Okay. Now, almost guarantee you that on a quiz or a test, all you're going to be given is that. You have to figure out what the graph looks like. Okay? So that means graphing calculators might come in sort of handy there, or just a quick use of graph paper just to see what the function is looking like. Plugging in values, whatever you can find to do to make that work. All right, let's do the last one, the C one here. It's a piecewise defined function, like I said before. What would you say is happening to it? Okay, I heard an increase. Where? Negative infinity to 0. Yeah, you use the x's there. Then it's constant from 0 to 2. Okay, now it's perfectly all right, especially since they give these here to put brackets there. But most of the time for increasing and decreasing, they'll use parentheses. But it would be perfectly legal to put brackets because you know it's constant between those two, 0 and 2, including. Okay? And then decreasing from, a little louder, 2 to infinity. Perfect, perfect, perfect. Y'all are good at this. Okay? Want to see how they do it? Okay, the A one, increasing of the entire real number line. You don't have to put minus infinity to infinity. I did just to show you you could. The second one was increasing from negative infinity to -1. I think we got that right. Second? Simpson, got it. Okay. Jemiah, right? Okay. Good deal. Anyone else come in when I wasn't looking? Okay. All right, so increasing from -infinity to -1, then, this is this one here, increasing -infinity to -1, then decreasing -1 to 1, then increasing again from 1 to infinity. Now, I'm going to tell you why I think they use parentheses. It's not a big deal, but why I think they do, okay? Because at this point here, at -1, it's changing, okay? It's not increasing anymore, it's not decreasing yet. Just past that, it starts decreasing. That's why I think they use parentheses rather than doing a bracket or on either one of those, okay? But it's not going to hurt you. It doesn't. I don't take off if you use the wrong symbol there, okay? So how about that third one? We had it increasing from -infinity to 0, constant from 0 to 2, and decreasing from 2 to infinity. And like I said before, you could have put, because of the way they define the function, you could have legitimately put brackets there. But usually when they're referring to intervals of increasing and decreasing, they usually just use the parentheses. So you don't have to worry about whether you put a bracket or not. All right, does that make sense? All right. To help you decide whether a function is increasing, decreasing, or constant on an interval, you can evaluate the function at several values of x, okay? And if every value you do seems to be going in the same direction, you can usually assume, yeah, it's either increasing, decreasing, or constant. If, when you're doing several values of x in that interval, and it is changing, you have to then figure out where that is. However, you need calculus to determine for certain all the intervals on which the function is increasing, decreasing, or constant. You may have a function that seems to be doing fine, but there's just a little place that it dips and goes back up. If you miss that in your testing, you might think it's increasing everywhere. Calculus lets you know for sure. You're not getting into calculus yet. That's why this is pre-calculus. That's why one of the things that calculus does, pre-calculus cannot. It can tell you exactly where those increasing, decreasing, and constant values are. Okay? That's just a plug to help convince you to get into calculus, right? Yes. It's a recruiting tool. Okay. The points at which a function changes its increasing, decreasing, or constant behavior are helpful in determining the relative minimum and relative maximum values of the function. So here first is the definition, then we'll see the graph of it. So what do we mean by relative minimum? That's not that smallest uncle you have, not that. Okay? The function value f of a, okay, this is f evaluated at some particular value a, is called the relative minimum of f when there exists an interval x1 and x2 such that a, and this is an interval from x1 to x2, and a is somewhere in between those that contains a, okay, such that for x1 less than x less than x2, in other words, this is the lower value, that's the higher value, that's how we write it. So to me this is almost redundant to put that in. But this implies that f of a is less than f of x for every x other than a. I mean, of course, it's equal to it. Oh, well, that's why they put the equal sign there. For everything in that interval, f of a is less than or equal to all the other f values. So your y's there are all greater than the f of a. So that's your minimum. Function value f of a is called the relative maximum of f when there exists some interval, x1 to x2, a in between those two, and for any x in between x1 and x2, every x in there, that implies that f of a is greater than or equal to the f of a. So f of a is the very highest value you can have. Okay? Now you might have several of them, or several minimum, either one, but nothing ever gets lower or higher than those. Those are your relative minimum and relative maximum. On a graph, they're pretty easy to tell, right? Okay? This would be relative minimum. So if you pick some x interval around that, every other value is greater than or equal to that. Okay? Relative maximum, because you pick any interval close to this value here on either side, and all those other values are less than or equal to that. Another relative minimum here. Okay? Now, what you don't want to do is pick a huge interval. Pick a relatively small interval right near that value. And you go down, and sure enough, every other value f of x for any value around that is going to be greater than or equal to that minimum value. And again, maximum up here. Any interval x1, x2 that you go around f of a, lots of f of a's here, then all the f values of those are less than or equal to that. Those are your relative max. Does that make sense? Okay. You will study a technique for finding the exact point at which a second degree polynomial has a relative minimum or maximum. That's going to be in chapter 2, I believe it is. Okay? For the time being, however, you can use a graphing utility if you have it, I mean a graphing calculator or something like that, to find reasonable approximations for those points. Okay? So if you have a graphing calculator, and by the way, whenever I do the book orders, I put on there that graphing calculators are permitted. So if you did or do have Pell Grant money left, you can purchase one in the bookstore. Now, if you already got your Pell refund, you can go out to Walmart, Office Max, somewhere like that, and get them a lot cheaper. But you can get them off your Pell Grant if you haven't already got the refund, which I imagine you have by now. Okay. Now, they're skipping example 5. Shame, shame. Let's see if I can, here we go. We'll put it here. Use a graphing utility, which you don't have, to approximate the relative minimum of the function f of x is equal to 3x squared minus 4x minus 2. Now, if you got a graphing calculator, by all means use it. If you got a computer that has a graphing package on it, fine to use, okay? If you don't, you might want to consider looking for one, okay? But if you're doing it by hand, all you have to do is get sort of close. What you do is pick some points, okay? What's an easy, my favorite of all time, x to use? 0. Yeah, y'all are thinking like me. Y'all are lazy, aren't you? Okay, good. So what is f of 0? That 0, that 0, negative 2. Okay. Now there you have a fairly small value. Okay? And this problem said to find the relative minimum. Now it may be less than that. Okay? It won't be more than that. Okay? But it may be less. So give me another x. That's another easy one. Fairly easy. What is f of 1? Yeah. Okay? All you do is put in 1 here, because 1 squared is 1, 1 is 1. So add your coefficients. What do you get? Say again? When you add the coefficients? Did you say 3 or 2? 3, except what sign? It's a negative sign, right? Negative 3. Okay, we're even less, okay? So we may be getting closer. So I wouldn't go any further this way. Now, here's why. This is a quadratic function. What shape is a quadratic function always? Parabola, exactly. So it's only going to have one minimum. So you know if f of 1 is negative 3, f of 0 is negative 2, you're not going to go down again. Because if it's negative 3 here and negative 2 here, it's only going to go up from there. Only. So let's keep going that way. So pick another value. Give me another x. 2. Excellent. And what would that be? Let's actually plug it in because this is getting... Yeah, come on back. Come on back. Okay, here we go. Okay. Yeah. This thing... All right. Started doing this kind of stuff yesterday. I think there must be a little short or something in the screen because when I write on the screen, sometimes that happens. All right, so this will be 3 times 2 squared minus 4 times 2 minus 2. Okay, so let's do this. 3 times what? What's 2 squared? 4 minus 8, negative 2. Okay, so that's going to be 12 minus 10, which is 2. Whoa, that went way positive, well, relative to the others. Okay, now I'm going to make a guess here. I'm going to guess, since it was pretty close here, way up there, that the minimum is probably somewhere between these two. So then I'll pick something between 0 and 1. Give me something between 0 and 1. 1/2 or 0.5, whichever you prefer. Okay. That would be 3 times, you prefer fractions or decimal? I don't care really too much. Huh? Decimal, okay. That would be 0.5 squared minus 4 times 0.5 minus 2. Okay? What is 0.5 squared? 0.25. Okay? Minus 4 times 0.5? No, 4 times 0.5? You may have said it right. I thought you said 0. 2. Excellent. Sorry, I can't hear well. And another minus 2. So this is, what's 3 times 0.25? Come on, 3/4 is 75 cents, right? You knew that. Okay, minus 4. So this is going to be minus 3.25. Hey, we did find something that was less, right? Now, which is closer to this or that? I would say this one, right? So I'm going to guess it's between 0.5 and 1. Pick something between 0.5 and 1. 0.75. Okay? Keep doing this. Okay? And you're going to narrow down until you an old mathematician way back in like the 2nd century BC named Archimedes. This is before calculus, probably before much pre-calculus and stuff. He started doing things like estimating the circumference of a circle, or area of a circle, one of those. And he kept doing different figures that he knew the measure of, bigger and smaller than the circle, kept getting smaller and smaller until he finally said, that's close enough. He called that method the method of exhaustion. Okay, so you do the same thing. Keep going as long as you want to until you get close enough and say, hey, I'm done. Okay. So let's just say it's going to be close to 0.75. Let's see what they got in the book. It's actually 0.67. No, I'm sorry. Yeah, 0.67 and negative 3.33. Okay. We were awfully close. Okay. If we'd have done 0.75, we'd have been even closer. Okay. Any questions on that? Okay. Okay. Give your point. Here's the x value. If I had stopped here, I'd have said the answer was 0.5, comma, negative 3.25. That's the point that is the minimum point. X, y. Alpha of x is y. Okay? So you're given the ordered pair, 0.5, negative 3.25. Okay? How far you want to go when you get tired of doing it. Okay? I want it as accurate as possible. If you have a graphing calculator, you can probably get really close. But if you're just doing it by hand, I wouldn't spend too much time on one single problem. If it looks like it's going to take a while, go on and finish the rest of them, then come back and continue working on that one until say, hey, that's close enough. And frankly, if you get, okay, this one, the last best guess was negative 3. This one is negative 3.25. When you get down to the point of, and the next one is probably going to be, you know, you could plug it in and see, it's probably going to be something either greater than or less than this, but then you'll keep narrowing it down. And like it will be between this and that, because we know the answer is 0.66. So finally you get to the point that these aren't changing much, it's going to be close enough. Okay? So how close you want it to be, that's up to you. But as long as they're not changing much. 0.25, that's a fairly big change. I would go at least one more time. And then if you say, it's still pretty close, go no. But after a while, say, okay, that's good enough. I'm going to stop. Okay. And that will do. Because not everybody has graphing calculators. Okay. Now, there is a checkpoint just like there is for every example they give. Please do the checkpoint soon after class, and you can go to larsonprecalculus.com and see an audio-video solution for those checkpoints. Okay. Any other questions on that? Good questions, by the way. All right, now we're going to move to average rate of change. Okay? We have learned that the slope of a line can be interpreted as the rate of change. Give me the definition for the slope of a line. Say again? Yeah, slope of a line. Okay, that's where the slope fits. So how do you find that m? What is the formula for m? y2 minus y1 over x2 minus x1. What is that saying? How is y changing when x is changing? The rate of change of y with respect to x. That's what we mean. It's a rate of change. How is y changing with regard to x? Now, that's for a line. What if you have a curve? Well, it's hard to tell what the slope is because it's always changing. Here it's slightly upward. Here it's less upward. Here it's 0. That was negative, okay? It's changing every time you move on that curve. So it's hard to say what's the slope of that. So for a nonlinear graph whose slope changes at every point, we talk about the average rate of change between any 2 points. The 2 points could be x1, alpha of x1, this we used to call, alpha of x1 we used to call y1, okay? and x2, alpha of x2, which we used to call y2, exactly. Alpha of x is equal to y. Remember that, okay? And so the average rate of change is the slope of the line that you draw between those 2 points. Right, here's your curve, okay? And you want the average rate of change between here and here, okay? Well, certainly it was greater, then it's lesser. So the average rate of change, draw this line between those 2 points and do alpha of x2, which is your y2, minus y1 over x2 minus x1.
Children's.
Say again? Oh, got it. Okay. That's exactly what we've been doing before, okay? So that will be the average. Here's your change of y for change of x. Alpha of x2 minus alpha of x1, y2 minus y1, that's the difference in y's divided by the difference in x, x2 minus x1. Just like you've done before. Nothing really too new here. Okay? Excuse me, hiccups. So the line through those 2 points is called the secant line. Okay? And the slope of that line is the m, that's what we use, mx plus b, m, but it's SEC because it's not the slope of the curve, but the slope of the secant line. So the average rate of change from x1 to x2 would then be change of y, alpha of x2 minus alpha of x1, that's y2 minus y1, over x2 minus x1. Nothing changed from what you did when you used to be doing slopes of lines. You're just doing the slope of the secant line. It's your change of y over your change of x, that's the slope of the secant line. Okay? Now, here's the problem. Find example 6. This is page 54. Find the average rates of change of alpha of x equal x cubed minus 3x. There's your function. From x1, which is minus 2, to x2, which is minus 1. So how would you find the average rate of change between those 2 x values? You got a few steps to do. Tell me one step you've got to do. Goodness gracious, come back. Come on back. Okay, where'd you go? It's nuts. Okay. Tell me one of the first steps you got to do. Okay. I hear something, but I can't make it out. Okay. Did you say that the function of y corresponding to each x? Is that what you said? Okay, yeah, let's do it. So let's do alpha of x1. What would that be? If x1 is negative 2, we're looking for alpha of negative 2. And what would that be? Here's your L function. What would that be? Help me, somebody. Negative 2 cubed minus 3 times negative 2. Okay. What's negative 3 cubed? Negative 8. Perfect. And what's negative 3 times negative 2? Plus 6. Negative 8 plus 6 is negative 2. So there's your alpha of negative 2. Alpha of negative 2 is equal to negative 2. Wow. They all won't be that way, I promise. Okay? What next? By the way, there it is right there. Okay, they had already done it for you. But, guess what? On a quiz or a test, I'm not going to draw the graph for you, okay? So you will need to figure it. That's why I'm having you do the calculations here. So, okay, say that one more time. Yeah, plug in each one. So plug in alpha of negative 1. That's your x1. I mean x2. Alpha of x2 is alpha of negative 1, and what would that be? Help me, somebody. Negative 1 cubed minus 3 times negative 1. What's negative 1 cubed? Negative 1 plus 3 is equal to 2. Okay, so that's your positive 2. So now what's your average rate of change between those 2 points? Average rate of change. Okay, that's my abbreviation for it. Between those 2 points would be, what's that formula we just had? Right here. Changing y for change of x, alpha of x2 minus alpha of x1. So what would that be? Alpha of x2 is 2 minus a negative 2 over say again, minus 1 minus a okay, yeah, let's do that. Okay, let's back off here. I'm going to erase what I did. Whoa, I didn't mean to erase that part. Okay. So erase what I flipped back there, but that wasn't good enough. Okay. The average rate of change, okay, is alpha of x2, that's your y2, minus alpha of x1, that's your y1, divided by x2 minus x1. Right? So what's the alpha of x2? 2 minus, what's your alpha of x1? Negative 2. Okay, over your x2, negative 1, minus your x1, negative 2. All right, let's do the math. What's 2 minus a minus 2? 4 over 1 minus a minus 2. 1. So that's 4. There's your average rate of change between those 2 points. Okay? Now, let's take a look at that. Here's the negative 2, negative 2. X equal negative 2. X1 equal negative 2. Alpha of x1 equal negative 2. X2 equal negative 1. Alpha of x2 equal positive 2. Draw the line between that. That's a really steep slope, right? Positive slope, going up, left to right. Positive slope, therefore, positive 4 looks like an excellent answer there. Okay? Okay? Now, let's do the second one. Okay? They're not going to use either one of those, so let me erase all my scratch here so we can start clean. Everybody got that? Anyone have a question before I do this? See, some puzzling and thinking and figuring. Everybody got it, or have any questions before I lose it? Say that again. Go to the next one. Is that what you said? Okay. I guess I just did. No. Okay. We're going to do the B part now. Okay? So you tell me what you need to do. Second, alpha of x1, is that what you said? Alpha of x1, with x1 being 0, one of my favorites, alpha of 0 is equal to what? Plug a 0 in here, and what do you get? 0! Okay, I like that one. Okay, let's go on and do my alpha of x2. And that would be alpha of 1, because x2 is 1. Okay, and what would that be? 1. Second? Yeah, negative 2. 1 minus 3 equals negative 2. See, what they did is 1 cubed minus 3 times 1. 1 minus 3 is minus 2. All right. We need to write down our average rate of change again. Not a bad idea. Average rate of change. What's that formula again? Alpha of x2 minus alpha of x1 over x2 minus x1. Change of y over change of x, just like slope has always been. Okay? Alpha of x2 was negative 2 minus alpha of x1, 0. I can almost do that one. And your x2 was 1, and your x1 was 0. Hey, I can even do that one maybe, okay? So what do you have here? Negative 2. Whoa, that's going downhill there, is that right? Sure enough, there's 0, 0, that's 0, 0, and here's 1, 2, 1, negative 2. It's a downward slope. Not as steep as this one was, it's still going down, so it's a negative slope, and it's going down 2 for every 1 at a time. Yep, that looks like that. I think I hear what you're asking, but this may not be, or my hearing's not good. When it's an increasing function, positive slope. When it's a decreasing function, negative slope. Is that what you're saying? Yeah. Oh, yeah. We could have done it on the graph, yeah. But because, I'm just going to give it away now. If I give you one like this on a quiz or a test, that's all you're going to get. You're not going to get the graph, unless you draw the graph, which would be fine. But that way you can figure it analytically or pick it up. You're absolutely right. You could have done minus 2, minus 0, over 1, minus 0. Same thing here. 2 minus minus 2, negative 1 minus 1 minus 2. Yeah, you could have done it that way. And if I wasn't planning to give you just that on the test, I would have let you do it. Okay, but I wanted you to be able to do it from scratch. Okay. So, good question, though. Excellent. Good observation. Let's see how they did it. The first one, we're going from negative 2 to negative 1 for your x's. So they did alpha of x2, which is alpha of minus 1, minus alpha of x1, which is a minus 2, over x2, which is minus 1, minus a minus 2. Okay? And that's why I asked you how you wanted to proceed, and you wanted to do each step first, which is fine, or you could have gone from the formula first. We ultimately did the formula, but after we had calculated. So that would have been, they don't show the calculations, it would have been a 2 minus a minus 2, just what we had, over negative 2 minus a minus. Negative 1 minus a minus 2 is negative 1 plus 2 is 1. Okay? So that would be 4 over 1. The secant has a very positive slope because the function was increasing in that interval. Okay. The B part, from x1 of 0 to x2 of 1, then you do alpha of 1 minus alpha of 0 over 1 minus 0, and that would be negative 2. They didn't show you how they calculated it, but they could have picked it just off the graph. Okay, and that would be negative 2. So that has a negative slope. All right. Now let me go back, because I do want to correct one thing if I was a little misleading. Certainly, if you're in a range where it's strictly increasing, it's going to be a positive slope. If you're in a range where you're strictly decreasing, it will be a negative slope. That's not the only way you can have a positive slope. If you pick this point to that point, it's still a positive slope, even though on this part it's increasing big time, this part is decreasing big time. So you can still get a positive slope and not be strictly increasing. So Well, I meant to say when you're strictly increasing, which you are here, you're always going to have a positive slope. When you're strictly decreasing, you're always going to have a negative slope. It doesn't mean positive slope means you're strictly increasing, because there's a positive slope, and it's not strictly increasing. It's increasing, then decreasing. So I wanted to clarify that because I spoke a little out of turn there. I didn't give you enough caveats. Okay. Now, one last little thing in this section, just the even and odd functions. What in the world do we mean by that? Anyone have a clue? Okay, we're going to learn. Here it is. You have studied different types of symmetry of a graph. Sure you have. Well, I don't know. Okay. The terminology of functions, a function is said to be even when its graph is symmetric with respect to the y-axis. That means if a function is doing something on this side of the y-axis, it looks exactly the same on the other side. In other words, every value on this side and this side, this side and this side, this side, they're all the same if you go the same distance away from the y-axis. That's called an even function, symmetric about the y-axis. In other words, the y-axis looks like a mirror. What you see on this side, you see the same thing on that side. Okay? That's what we mean symmetric about the y-axis. That's an even function. It's an odd function when its symmetry is with respect to the origin. Now, let's wonder what in the world they're talking about. Well, what they mean there, if when you go left of the origin, you're going down here, right of the origin, you're going to go up there, but the same amount. Or left of the origin, you go up, right of the origin, you go down, but by the same amount. Okay? That's called an odd function. So the symmetry tests yield the following tests for even and odd functions. Either you have to graph the function and hope your graph looks close enough to reality that you can tell, or doing it analytically, here's how you do it. A function y is equal to f of x is even when for every x in the domain of that function f, if you put the negative of x in there, you get the same value f of x. In other words, when you do for this value x, here's your f. When you do negative x, you get the same value. Okay? F of minus x is the same as f of x. That makes it an even function. If for every x you put in there, that comes out. But then if a function is odd, if for every x in the domain f of negative x, okay, so here's your f, there's your f of x. Here's your x, there's your f of x. When you put a negative x in, same distance away, you're going to be the same distance down. That makes it an odd function. Or, when you come over here, it's down here. When you come over here, it's going to be up there. For every x in that domain, f of negative x is the opposite of f of x. That makes it odd. Now, they left out one important classification of functions. Anyone think of what they would be? A neither function, okay? Not all functions are even or odd. A bunch of functions are neither. Let's just go back to a few graphs, okay? We'll come back in a minute. Okay, this one, you want to make a guess at it? Even or odd? Or neither? It looks like it's odd because you go to negative 1, you're up here. Positive 1, you're exactly opposite down here. If you go to negative 2 here, positive 2, you're up here. Exactly opposite. So sure enough, that's reflects across the origin. That's an odd function. Okay. Want me to tell you a little cheat? Look at your exponents. What's your exponent here? 3. What kind of number is 3? Odd. What is your exponent here? 1. What kind of number is 1? Odd. If all your exponents are odd, you're going to have an odd function. Now, that's for polynomial functions. Other functions you can't tell. For polynomial functions you can. Let's go back a little further. How about that one? That's a neither, okay? You can't see them much, but when you go over here, you're up here. When you go over here, you're down here. Those are opposite of each other. It's going in the opposite direction. This is a positive number, that's a positive number. They're not opposite each other. So that's a neither function right there. We don't know what the function is, but it's neither, okay? How about that one? Neither also. You go a little bit this way, you're down here, a little bit this way, you're up here, but those are not opposite each other. They're both negative, both positive. So that's a neither. Most functions are basically going to wind up being neithers. Not always, okay? How about this one? Odd, because, yeah. How about this one? Odd. How about this one? Neither, okay? Can't find the even one, can we? Okay. What's that one? Neither. Ooh, so close. But it's not quite even because the vertex is down here. It reflects across here, but not across there. You can tell that because you go 2 to the left here, you're at 0. You go 1 2/3 here, and you're at 0. That's not going the same distance. So that's a neither. Almost even, but not. Okay? That, okay, that looks like it might be odd. No, I'm sorry, that looks like it could be even. I can't tell, but if this on this side is equal to that on that, it doesn't quite look like it is. It looks like this is a little closer than that. But that's awfully close to being even. You just can't tell what's happening down here. Oh, no, this is odd. This is a neither. Here's why. Because remember, for every x in the domain, well, 3 is in the domain, there is even a -3 here. So that has to be a neither. Sorry about that. Okay. And that's the same one. That's a neither. Whoa. What would that be? Now that has some hope for being even. I think that's a neither also. Okay? See, it's so easy to get a neither. I think we're just about through. Okay? Let's go back to where we were. And they're going to give us some. Do we have all those? What's that one? This one didn't show up before. That's an even function, isn't it? Same thing on this side as that side. We finally found an even. There it is. Okay. I knew we had one somewhere. That one? Neither. Oh, that one? Neither. And we already did those 3. That one? Neither. That one? Neither. That one? Odd. Excellent. Okay. All right. So those are the tests. Real easy. Hey, guess what? You do the same thing to both ones. You're given a function, just plug in a -x and evaluate what alpha of x is. If it's the same as alpha of x, even. If it's the opposite, you plug in the same thing here. So if it happens to be the opposite of alpha of x, odd. But if it comes out something that's neither one, it's a neither. Okay? That's your test. Plug in -x. So here's what we're going to do. And I hate it they show it to you already. Okay? Just pretend this isn't here. Okay? Pretend that's not there. Okay? What's your test? I don't want them telling you. What's your test? Plug in -x. And what is -x? G of -x. Negative x cubed minus a negative x. What's negative x cubed? Negative x cubed. And what's minus a minus x? Plus x. Okay? Now, what you do is compare. How does this g of minus x compare to that? Exactly the opposite. You put a minus sign here, that makes that a plus, and that a minus, that's what you got here. Exactly the opposite. So therefore, they're right. This is an, what kind? Odd function. And what's the other cheat test? Look at your exponents. 3 and 1, both odd. It's an odd. Okay? All right. I think I will erase some of my scratch here because I did a lot of scratch. Okay? And when you plug that in, you get negative x cubed plus x, which is exactly the opposite of g of x. So that has to be a negative. You factor out a minus sign. Okay? That's exactly the opposite of x. So therefore, it's an odd function. All right, forget this one. Okay, sure. Oops, that. Sorry, I get carried away. Someone let me know how we're doing on time. Got 5 minutes. Okay, I think we'll finish this section. All right, time to move. All right, let's do this one. What's your test? H of negative x. What would that be? Negative x squared plus 1. What's negative x squared? X squared plus 1. Same thing. H of x is the same as h of negative x. What does that tell you? Even function. Absolutely. And here's the other test. What's the exponent here? 2, and what's that? Even. What's the exponent here? Well, there's not 1, or it's 0. X to the 0 is 1. No, x to the 0 is 1. Anything raised to the 0th power is 1. So that is also an exponent. That's the exponent of 0. What kind of number is 0? Even. Even, Stephen. Okay, no, okay. That's an even function. Right? All right, but the test is to plug in the minus x, which we did, and they gave you x squared plus 1, which is exactly h of x. That's the test for an even function, and it passed. Okay. Make sense? Here are examples of those. Here's the graph of it. Here's that first one. It's exactly an odd function because it's reflective across the origin. Okay? Whatever it's doing on this side, it does the opposite up there. Okay? This is an even function because it reflects across the y-axis. So the other way to say this is it reflects across the identity function. Y is equal to x. Okay? Whatever it's doing here, it's doing there. Not quite close. Okay. Whoa! Could we be at the end? Yeah, there is a checkpoint. And now what they didn't show you is an example of a neither function. But look down at your checkpoint. Do you think any one of those is a neither? Anyhow, have you got your book still open? No, you already closed them all up, didn't you? Okay. Do your checkpoint. Homework exercises here includes any of the odds, 7 or 9, both at Calc Chat, 9's at Calc View, 11 or 13, both at Calc Chat, 11's at Calc View. Any of the odds, 15 to 25, they're all at Calc Chat, 25's at Calc View. Any of the odds, 27 to 31, they're all at Calc Chat. 33 to 39, they're all at Calc Chat, 35's at Calc View. 43 to 47, all at Calc Chat. 49 to 53, all at Calc Chat, but 51's at Calc View. 55 to 59, all at Calc Chat. 57's at Calc View. 61 or 63, both at Calc Chat. 61's at Calc View. Then you can do number 65, it should be a calc chat. Then either 67 or 69, they should both be at calc chat. Any of the odds 71 to 75, all at calc chat. 71 is at calc view. 77 to 81, all at calc chat. 83 should be at calc chat. 85 should be at calc chat. 87 you can do if you'd like. It should be at calc chat. 89 should be at calc chat. There's a couple true false. 91 or 93, both at calc chat. You can think about doing 95. It should be at calc chat. 97 is a writing. If you want to play around with that, you can. It should be at calc chat. But 99 is one of those even and odd or neither. That should be at calc chat. There's 4 of them down there. Check them out.
Before there's a piece of paper going around. If you guys put your name and number on it, we can make a group, and we can make a group chat. And
What's that?
You know STDs.
I'm sorry?
This statistics is
Okay, now what's your question?
I don't know.
Oh, you're doing the statistics? Okay,
It's business.
okay. All right, and this is your data set, is that right?
Yes.
Okay. Now, what you trying to figure out exactly okay. So this would be like X and like Y's. Okay. And they put them on an Excel data file, it looks like. It says determine the first and the third quartiles. Okay. They've already done the first quartile for you.
I got the.
You got it. And how did you get that? Okay.
Because it was, I put in 34 and it wasn't right. So
Okay. So you did it by trial and error. Okay. Okay. Here's how I think. Now, I don't know how they taught you to do it.
this is an online class.
Yeah. Oh, you mean you're not doing the,
This is an online class. So
you haven't done anything in the class? Okay. Well, I don't know where it's coming from, but here is your range of outputs, 41 to 82. Okay.
And the mean is 49. The median 49.
Median is 49. Yeah, all righty. Bye-bye. This is the median value, but your quartiles, are they based on median too? Then that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? The middle one would be 1, 2, 3, 4, 5, 6, 7, 8. Median would be there. Your first quartile, okay, I'll try not to do these correctly. 1, 2, 3, 4, 5, 6, 7, 8. So it'd be in between.
So it'd be like 41.
Okay. I don't think it's based on median. I don't think it's based on that. I think it's based on average. So I think what you have to do is average these together. You add all these up, and then divide by however many you had. What was it, 15 or something like that. Get your average value. Okay? And then I can't remember if you do the average of the ones down here, and that would then make your mean. And here's why it's coming out strangely. because you see, these are all close to each other down here. But these are way spread out here. So this is pulling it way higher than what you would expect looking at the median, okay? So I think if you do it by averages, you see that's what's dragging it up and making the, you average these, but then you pick the point here that corresponds to that. So it's here because, and that doesn't even look right either. Yeah, it may be, because between 41 and 82, there's 41 in between that, and then, so 41 and 40, okay. And half of that would be 20 and a half. So that would be 61 and a half. So you see your mean is somewhere right in there. Between the mean of all these values is right in there. And the median then would be somewhere probably right, the first quartile somewhere here. The third quartile is going to be somewhere between, if this 33 is right here, then you do the, I'm just going to make a guess here, that would be about 41 to, I'm just going to guess, 48, so that would be about 7 from here. 7 from here would be 75. I think it's going to be like 37 point something. You know, because you're going, the mean between these two is, well, I can't say mean, but it's somewhere around, between these two is somewhere right around, there's a difference of 41 there, and half of that would be 20 and a half, so that would be 61 and a half. Okay, so that would be right around there, so that would be the mean, somewhere right in there, and then the first quartile, which would be a quarter of that, would be somewhere down here. So that the 33 makes sense there. That makes it, just judging from that, I don't know. $37 and some fraction is what I would guess. 37 point, yeah. So that's rather bizarre. Now, is this a course you're taking here?
Yeah, it's business statistics.
Business statistics. Okay, do you have a book with it?
It's
E-book?
E-book.
Okay.
But I can't really learn from it, but like I have to learn like in person.
Right. Who is you taking that under, Mr. Armbruster?
Yes, sir.
Okay. Go see him. I think he can tell you exactly how they're doing this.
Where's his office?
Oh, it's right outside. If you go down this half flight of stairs right outside the door here, and then take immediate left and go up one flight of stairs. Then when you come around the corner from the stairwell, first office on the left, I think it's 360 or something like that, his office is inside that classroom.
Appreciate it.
Yeah, so he's real close. And I think he'll be quite willing to help. Sorry, I couldn't do any better.